talk to you about containerizing your geospatial server for scalability at the tactical edge with LuciadFusion and Docker. Mouthful there, I know. So containers is really what we're going to talk about, not the kind of containers at the Suez Canal a couple of weeks ago, but different kind. So we're going to talk more about that. But yeah, my name is Brian Moran. I'm coming to you from Washington, D.C. I'm a solutions consultant at Hexagon. I joined Luciad in 2014. So I've been working with customers and prospects to build solutions using the Luciad portfolio for almost 7 years now. And I'm excited to share with you some kind of under the radar, but I think very important features for our server product, Luciad Fusion, today. So if we have a look at the agenda, we're first going to do a quick dive into the Luciad portfolio and Luciad Fusion in particular. We'll discuss the benefits and architecture, as well as a quick overview of some of the front-end features. Next, we'll discuss different deployment strategies and how Luciad Fusion is capable for a modern multi-node deployment. And once we have that concept explained, we're going to take a look at containers and how we can containerize our Luciad Fusion server, specifically with the Docker container engine. And then finally, we'll discuss some advanced topics like orchestration and scaling, really bringing together the concepts of multi-node and containers. So to step back, the Luciad portfolio really is a set of platforms and toolboxes to build situational awareness and real-time location intelligence applications and systems. The tagline for the Luciad portfolio for some time has been connect, visualize, analyze, and act. When we're talking about connect, we mean directly connecting to over 200 data formats out of the box with an open API to develop new connections to any type of data format. This is a pretty unique capability in the geospatial realm because we're not enforcing any type of ETL or vendor lock-in. We want to leave your data at rest and in its native format, if at all possible. And amongst these 200 data formats, we're talking about common stuff like shapefiles, geotiffs, geopackage shapefiles, PostGIS, Oracle Spatial, all the greatest hits of your GIS data formats, as well as domain-specific formats like AIXM in the aviation sector, maritime charts like S57 and S63, or in the defense domain, formats like NIDIF or NATO vector graphics we support. And then we also support 3D digital reality data sets such as point clouds, photo mesh, and panoramic and street view imagery. When we're talking about analysis, we're talking about the client, kind of the client side of things, where we support GPU-enabled visualization and analysis. As you probably know, most every device nowadays is going to have access to a GPU-based rendering in some way, including your mobile phone. Luciad APIs leverage this automatically with no plugins, but also maintain the capability to fall back to a CPU rendering if for some reason a GPU is not available, but this is becoming rarer and rarer. Yeah, and also highly accurate coordinate transformations is something we pride ourselves on as well. And then visualize, Luciad supports both 2D and 3D, and of course 4D natively with configurable styling options for your data. Additionally, the visualization parameters can be tweaked to give a realistic representation of the globe, think like sunlight at a certain type of the day or shadows for 3D buildings, among other things. And then ACT. Luciad offers intuitive map-centric user interfaces, which allow users not to just visualize data, but also interact with it in terms of editing, creation, filtering, you name it. Additionally, the Luciad portfolio, for sure, we're talking about the defense domain here, it maintains a mission-critical focus. So we support military data and symbology standards like the NATO APP6 standard, as well as the US military standard 2525 symbology. And then also all of our software is binary backwards compatible, meaning you can have very easy and smooth upgrades from one version to another. And that's, super vital for long life cycle defense programs. So if we take a very quick look at the architecture of the Luciad portfolio, again, you'll see connect, visualize, analyze, and act. And on the bottom, you'll see all of those data connections we talked about, databases, files, web services, all that kind of good stuff. It then is generally going to be cataloged by our Luciad Fusion server. Basically, Luciad Fusion is made aware of where that data is so that it can publish web services, including Open Geospatial Consortium compliant web services with just a couple clicks. And then on the top, we have our client-side libraries. Like on the desktop side, we have Luciad Lightspeed, which is a rich Java API for building desktop applications. We also have Lucid C Pillar, which is geared more towards C++ and C# frameworks like Qt. And then in the browser, we have Luciad Ria, which is a pure HTML5 visualization library for building 2D and 3D map views using JavaScript and TypeScript. It can integrate into, the front-end framework of your choice, whether that's React, Angular, Vue, even something like Svelte, or no front-end framework. So we're agnostic to that. And of course, it's providing that browser-based visualization without any plugins. And then we also have a mobile framework that's really geared towards the disconnected soldier called Luciad Mobile, and that's a native Android API. So I'm going to switch to a quick video so you can get a feel for some of the capabilities here. This is going to, I want to restart that. Yes, restart. Okay. So you should be seeing kind of a web-based user interface. This is called LuciadFusion Studio. It's the web front end for LuciadFusion server. It allows you to manage all of your data formats. Basically, everything starts with this concept of data routes, which are essentially locations either on your local file system or a network share or some shared disk where all of your data lives. So what happens is you inform LuciadFusion of these different data routes. It goes and crawls those locations on, maybe some type of schedule or kicked off by a REST API call. It harvests all the metadata, and all of the geospatial bounds and all that kind of stuff, and adds it into a, let's call it metadata catalog database where we have, all of our data tracked to know what we have available to create services from. So here we're just showing, you can make a schedule to run this crawl job, but once that data is imported, the data is still in its original location, but we can start to preview that data, take a look at it directly in the browser, but then also take these data files and create a web service on the fly. So we've got over 300 ECW files, imagery, data. We're gonna create an OGC WMS from that with just a couple clicks. So here, just, giving the endpoint a name. You can choose the type. If you wanted to do WMTS or something like that, you could do that as well. And now really with what was that, I don't know, 2 or 3 clicks, we have a published WMS with no pre-processing or anything like that, ready to be consumed by any OGC compliant client. Luciad Ria is one of those OGC compliant clients. And of course, all the Hexagon products are going to support those protocols, but other vendors, of course, will have those as well. And so we can take that endpoint and drop it directly into our browser application and visualize it on the map here. So, we have originally some Bing Maps imagery here, but now that we have our new Berlin imagery, we're going to overlay it on top of that Bing Maps imagery because we have our higher res imagery now. But this is the more, let's say, traditional geospatial formats, but we also do really well with, 3-dimensional data, data we would call digital reality or digital twin data. So this next video we're going to show here is showing some photogrammetric data, reality mesh data that was captured from an airborne sensor, showing a 3D cityscape, but also integrated into the same view is panoramic or street view imagery. And what's unique about this is it's all in the same viewer, not some stovepipe street view viewer, so that we can do nice 3D measurements directly on our 3D data while also still having the context of that panoramic imagery. And of course, we can bring our other asset type information into the fold as well when we're talking about like let's say some underground assets like pipelines and things like that, and see those attributes all in the same integrated viewer. That's really one of the big benefits of the Luciad platform, bringing all these disparate data types together. And of course, we're talking about defense. So recently with Luciad Ria and LuciadFusion, we've got a prototype decoder for NATO friendly force information, NFFI data, which is a real-time format for sharing the real-time position of friendly forces to different coalition forces. When you have multiple countries working together on an operation, you want to make sure where everyone is to minimize things like friendly fire and things like that. So, we have that data moving around real time on the map. And then of course, with the correct military symbology, whether you want APP6 or MS-2525 or whatever you want. So if I hop back over to, oops, sorry, we don't want to see me yet. I want to share my screen. So if we move past this video, let's talk about what we're really here for, which are deployment strategies and techniques. So first, a quick explanation of this simplified architecture diagram. We'll start on the right, where we have all of our data sources. Those are those data routes, locations where our data lives. This could be a local file system, network shares, or database connections. We then inform the Luciad Fusion Studio application, and then this is then stored in our catalog database. From there, we can also kick off pre-processing jobs or publish services. All of this, again, being stored in our catalog database. So now we have different users actually interacting with our server, doing some administrative tasks like publishing different services, and then actually consuming some of those service endpoints. But what we're seeing here is a single node deployment. You have a single server providing all of the services necessary to service your clients. For a lot of use cases, this might be just fine. For example, in a forward deployed scenario, like on a boat, an airplane, or in the field, you need something that can be quickly started and stopped and potentially on even limited hardware. However, if we're talking about a distributed deployment of any kind in a mission critical environment or anything that we're servicing hundreds or even thousands of users, this is not really gonna fly. So we've introduced a single point of failure for our system. So any goal of high availability or reliability are essentially gone. Even if there's not an error or an issue that causes downtime, we're still gonna experience downtime whenever we wanna upgrade our server or scale it up or scale it down. So the alternative for these more demanding use cases would be a multi-node deployment, sometimes referred to as clustering. Essentially, we're taking 2 or more servers and grouping them in such a way that they behave as a single server. So what are the benefits of that approach? Like we mentioned earlier, we can achieve higher availability with a multi-node approach. Even in the most simple scenario, we could have, let's just say, 2 nodes with one failover node ready to take over if a health check fails on our primary server. We can check out, we can more strategically assign and utilize our resources. For example, we may not want to burden our primary service endpoint nodes with pre-processing or geoprocessing tasks. We could have those delegated to specific nodes that have more appropriate resources. A buzzy term we've been hearing a lot in the past few years is microservices. I'm not usually a huge fan of buzzwords, but I believe this one has some merit. The goal is essentially to break down an app into its core functions. These functions can be deployed independently, meaning individual services can function and fail without negatively affecting the others. And of course, an obvious benefit that we'll talk about a little bit more is load balancing and scaling. We can try and distribute network traffic and loads across multiple nodes so that our deployment remains stable. We can even implement some auto scaling characteristics if certain thresholds are reached, and perhaps even spin up more nodes. There are a lot of other benefits, but of course before we move ahead, we might want to ask our question, an important question. Is my application stateless enough? And what do we mean by stateless? A stateless application is one that neither reads nor stores information about its state from one time that it is run to the next. So I think you can see why this is important in a multi-node application. We can't have stateful information local to our node, or else we wouldn't be able to spin up new ones. Remember, when I'm presenting things if we're talking to a single server. So what about our Luciad Fusion nodes? I wouldn't go as far to say it's completely stateless, but it is, I think, close enough to have a pretty compelling multi-node deployment. The 3 main tasks that Luciad performs really only depend on 2 things. It's the catalog database, so whatever data sources are referenced in the catalog. And then a distributed deployment, our database server will most likely be on a separate instance, likely a cluster, database cluster of its own. And our data will likely, that data that it's referencing will likely be network accessible in some type of redundant network storage. So as long as our node can access these resources via the network, we're free to create as many as we please. So now let's take a look at what a multi-node deployment could look like with Luciad Fusion from a pretty high level. We still have our different clients accessing our services over the network, but now we have a reverse proxy or load balancer in front of our different nodes. This could be something like Nginx or Apache HTTPD, or perhaps a cloud native solution like AWS Elastic Load Balancer or Azure Application Gateway. But essentially that load balancer is sending specific workloads to specific nodes. We have node 1 that is specifically taking care of OGC and other services, while node 2 is also handling administrative duties and pre-processing. But really, we could have as many service nodes as we need because they're all reading from the same Studio or metadata catalog database, which is referencing the same files or database connections over the network. To get to this attainable goal of multi-node deployments, the application ecosystem has come a long way, from traditional bare metal deployments on a server to virtualization and virtual machines. Now to containers, which actually have been around for a while, with like Linux containers and free BSD jails. But they've really gotten popular within the last decade due to the rise of Docker, which you've probably heard of. And basically the main idea is containers allow us to decouple our application from the underlying infrastructure. So it's going to be portable across machines, across clouds, across operating systems. So again, why containers? We've talked about some of this, but why are they advantageous way to deploy software? Well, first and foremost, they benefit your developers more than anyone. I'm pretty sure every software developer has uttered the words, it works on my machine at least once. So having to maintain different versions of dependencies, environment variables, security, and permissions becomes quite a bit more manageable when you can isolate into a single process service or into a container. This, of course, ties into that concept of portability again. So, okay, now we can deploy into production on different operating systems and in a cloud-native fashion, decoupled from the infrastructure. But our developers, again, can have a predictable experience too, regardless of if they're developing on Linux, Mac, and yes, even Windows. Windows support for Docker has come a long way with the help of Windows subsystem for Linux. All these concepts too tie in nicely with the DevOps strategies of the day in terms of continuous development, integration, and deployment. In general, you can consider containers to be more lightweight because you're sharing the machine's operating system and kernel. And you might have already started to guess, this actually fits pretty well into our microservice paradigm that we mentioned earlier. And of course, we're isolating our resources and processes. So, a resource-hungry service hopefully will not negatively impact another. So let's try and throw Luciad Fusion into a container. But first, maybe we should actually take a look and a second to understand what Luciad Fusion is from a technology stack perspective. At its core, Luciad Fusion is a Java server application based on the Spring framework. It's ultimately deployed and delivered as either a WAR file that can be deployed into an existing servlet like Apache Tomcat, or we also can provide a kind of like standalone executable or application that is bundled with a Jetty servlet. This is what we're going to use for our implementation here. But if you have a look here on the right, it's really just a series of jar files and YAML configuration files. So where to begin? We know that Luciad Fusion is now based on Java, but what now? Docker has a pretty rich ecosystem of images for many popular languages, applications, and operating systems. As you can see here, we've got an official Node.js image, PostgreSQL image, and then also a Java, OpenJDK image. And we can start from that OpenJDK image and use that to extend for our Luciad Fusion container. So now we need to create a Docker file for Luciad Fusion. A Docker file is how Docker knows how to build an image. It'll read this text document, execute the commands, and create our image. You can see that we're first going to extend from an OpenJDK image. Next, we copy over the actual content of our Luciad Fusion server over into some location inside the container. Then we run some commands to create a user and a group that's actually going to run the process within our container. That's kind of like more of a security concern because we don't want the root user to be running our process. Then we define a working directory, expose some ports, and then actually define the command that's going to run when the container starts. And that's kind of an important thing to consider because the container is only going to run as long as this command keeps running. So when that server stops running, the container itself will stop running as well. And on the right, you just see some of the Docker commands where we're building an image, creating a tag for it. A tag is basically a descriptive way to describe what you have. So we have our Fusion server. Maybe you create different tags for it, one Java 11 tag, a Java 8 tag, an Alpine Linux tag, what have you. So now we can go ahead and run our container, since we have our image, which maybe we've also, pushed to some container registry that might be available in our ecosystem. But we have a few options here that we can, further customize what we're doing. We can map the host port, a port on our host machine to a port on the container. So Luciad Fusion is running on port 8080 by default. This may or may not be necessary in your environment. For example, you might have a reverse proxy within Docker. That's the entry point to your container network. But for our purposes, we'll expose that port. Next, we create a couple of bind mounts, which are mapping a location on our machine's file system to the container's file system. So in our case, we want to give like a data root. This could be one of many data roots, but essentially this is where our data lives on the network. We also create a bind mount for a data store, which is essentially data that's going to be shared across our different Luciad Fusion nodes. Specifically, these are like caches and preprocessor outputs. Additionally, just kind of like a bonus, it's nice to note that Spring has really good support for environment variables within its YAML files. Environment variables are pretty popular ways to customize a Docker container because you don't have to actually rebuild it, but you can customize some of the things that are going on. It's also like a nice way to inject secrets like database credentials and stuff like that. But this is obviously a very simple example that we're doing here. Customization possibilities are endless. We're really giving the developer and the customer all the tools they need to enable them and build it to match their environment, really. So yeah, we've containerized our server, and that's pretty awesome. Our DevOps and developers are thanking us, and maybe some of this information is already common sense to you, but hopefully it's been informational to some of you. But really, it's just a gateway. We can actually take the next leap with what we've talked about here and adapt it into container orchestration solutions like Kubernetes and Swarm. Especially Kubernetes, which really is kind of the tool of choice nowadays, helps with some of the concepts that we've already talked about and more, like load balancing and some of the DNS challenges that come with that. Storage orchestration, including integrations into a lot of existing public cloud solutions. It can also restart and replace containers that fail or don't respond to your health check, what we call self-healing. And as you would guess, there are also auto-scaling solutions when you have spikes in demand, nice stuff like secrets management. And really all we're trying to do here is zero downtime deployments. That being said, there are a lot of solutions out there to help, like OpenShift and Rancher, which are actually built on top of Kubernetes. And then all of your major cloud providers like AWS, Azure, GCP, they all have Kubernetes as a service offerings available. But like you guys, some of you probably know, that's a topic that's going to take way more than 20 minutes, which I think I've already breached. But so we'll leave that for another day. And if you want to take a look, all of our documentation is online, dev.luciad.com. Some of what we've talked about here is going to be there, but there's some nice videos and demos there as well. So if we still have time, that's what I had. I don't know if there's any questions.